Welcome to Brain Vision.
Compton scattering is an elastic collision that usually is studied where you send in highly energetic photons, either X-rays or gamma rays, into matter. And they presumably scatter off of electrons that are nearly at rest, thereby exchanging both momentum and energy with that electron. So the electron is assumed to be at rest. Being an elastic collision, the idea is that both momentum and energy are conserved. And that is the momentum and energy of both particles. Now, it turns out if you have relativistic, if you have gamma rays, well, let's start off with X-rays. If you have X-rays, you can use classical formulas for both momentum and energy. However, if you have gamma rays, you need relativistic formulas. So often the discussion to begin with is around X-rays scattering off of electrons. So here we're going to take as an example a photon in the X-ray range starts off with 0.0780 nanometers. And it does what's called Compton backscattering. This is often the feature that's detected in a detector. But in that, the maximum energy and momentum are transferred into the electrons inside the material. Now, it turns out that we could start and, just here, I'll just show it. Here comes lambda initial, lambda final, goes straight backwards with a new wavelength. We could write down formulas for momentum and energy. But it turns out that it's a little bit easier if we start with the Compton scattering formula. As a function of the scattering of the X-ray is simply given by lambda final minus lambda initial is equal to h over the mass of the electron times c times 1 minus cosine of phi. And here we have phi equals 180 degrees. So once we determine the final wavelength that comes out, we can say that the change in energy of the photon is equal to hc over lambda initial, the initial energy, minus the final energy. And we're really doing a absolute value there. And that has got to be equal to the kinetic energy of the electron, which is Pe squared over twice the mass of the electron. So I am going to use atomic units here. The mass of the electron is 0.511 times 10 to the 6th eV over c squared. And we're going to take hc as 1240 eV times nanometers. And we're going to start with a lambda initial equal to 0.0780 nanometers. So we're definitely in the X-ray region, and we don't have to worry about that relativistic momentum energy formula. So the lambda final is going to be larger than the initial. And let's go ahead and write that down. Lambda final is equal to 0.780 plus HC over MC squared times 1 minus cosine of 180 is just 2. And the second term is 1240 times 2. EV nanometers divided by 0.511 times 10 to the 6th EV. So we see that the units are, of course, in electron volts. And that is 4.85 nanometer. Whoops, let's see. Go ahead and write this 0.078 nanometers. That's actually in the picometer range. 0.048 nanometers. So that is 0.0829, we'll say, nanometers. So yeah, it has a longer wavelength because it gave energy away to the electron. So now we can go ahead and solve for the kinetic energy of the electron. Okay, so the Ke is equal to Pe squared over twice Me, and we'll multiply by C squared in the top and the denominator. And now we'll take the difference between the two wavelengths at their inverses. And that will come out in units of electron volts. Uh, 940 electron volts. And so we'll go ahead and solve for that constant Pe squared. And we're going to take twice the energy of the rest mass. 0.511 times 10 to the 6 EVs. So this will give kind of a weird unit here, but it is one that gets used a lot. PE times C is about 31.0 EVs. And so PE is 31.0 EV over C. And whoops, let's see, that's times 10 to the third. Yeah, oops. So that's kilo electron volts. And we could multiply by 1,000 volts per kilovolt, and by the charge on an electron, 1.6 times 10 to the minus 19 joules per eV. And then we could divide by convert C into times C is 2.99 times 10 to the 8th. This is getting a little sloppy, so let me let me just do this in a couple steps, but yeah. So that's 4.96 times 10 to the minus 15 joules per C. And now we can turn that into 2.99 times 10 to the 8 meters per second. And a joule divided by a meters per second will get us the SI unit of momentum. So that is 1.66 times 10 to the minus 23 kilogram meters per second.